So I'm very happy to be here. I'm Newell Washburn from Carnegie Mellon University. I have a startup company called ANSATZ AI, and I'll tell you a little bit about that at the end. Most of my talk concerns a more sustainable binder for concrete called limestone calcined clay cements. The goal is to reduce about at least 50% of the clinker with a combination of limestone, calcined clay, mostly based on kaolin, and gypsum. The main challenge with this, though, is that the flow of the paste is significantly curtailed particularly through the effects of the clay. The more clay, the higher the yield stress and the higher the plastic viscosity. And so we were interested in developing a model for mostly for starters, just understanding the basis for this. In comparison with Portland cement, there was a nice study that came out a few years ago that clearly demonstrated that there was a direct proportionality between the evolved heat beyond the onset of the acceleration period in Portland cement. So where the hydration really starts to take off is here. There's the rate of heat evolution is basically directly proportional to the yield stress of the paste. The interesting thing in this study was that they showed that this scaling relationship held even for different average particle sizes, suggesting that it was holding for even as a function of the specific surface area of the cement. Of the Portland cement in this case. When we attempted to reproduce that, we tried 3 different limestone particle sizes, 3 microns, which is on the small side, and then 15 and 25 microns, which are more standard. And certainly for the coarser limestone particles, we saw sort of a relationship, but there was a different relationship for the 3 micron. And so what that suggested was that we didn't have the same sort of scaling or sort of size independence of the scaling relationship, that there were different forces at work that governed the rheology of LC3 paste. And so we were interested in how can we predict this yield stress as a function of composition. The thing that we're really going to talk about, though, is just what are the forces that govern it. There have been a lot of separate studies on the factors that govern the yield stress or the rheology of LC3 paste. And the reality is that all the good ones are all correct, even though they've all looked at different factors. So one group was looking at the effect of different zeta potentials of the clays and their impact on the rheology, and they saw a clear trend where zeta potential was a strong factor. We were looking at, we separately were measuring, and this is in the paper that's is being re-reviewed right now, I think, that there are certain trends. Certainly as we increase the amount of water present in the paste, we see a decrease in the yield stress. That makes sense. The greater the relative proportion of clay, so 30% is in blue versus 15% is in green, we see an increase in the yield stress. That also makes sense. So all these factors are important. And the question is, well, how can we want to build a general predictive model for LC3 rheology. We'd actually like to be able to use machine learning, but we're only going to have 50 samples. Is that even possible? Really the goal of machine learning is to predict the properties or the response of a system given a certain set of input parameters. And so, like in Pittsburgh, you always have to look carefully when you're crossing the street because there are a lot of autonomous vehicles that are being tested. But this is being used in finance, it's being used in medicine, et cetera. And so we were interested in being able to use this in the context of materials design in particular. And so the requirements are, one, you've got to have data, and you need to see trends in data. So like up there on the top, I show that's the mini slump of LC3. So for increasing coarseness of the limestone particles, what you see is more spread that makes sense. And so we see clear trends in the data, check. And then also, excuse me, no analytical model. Particularly, I mean, there are analytical models governing things like mini-slump or yield stress of paste, but they're not parameterized by composition. They're parameterized by other parameters. And so the basic message for the last one is if you've got an analytical model, use it. If you don't, then you're probably stuck doing machine learning. So in machine learning, the models really capture patterns in the data. And all the math that's going into it is, so you've got your data, you put that into a spreadsheet. There's a bunch of math that tends to happen in these algorithms, and what's going on is the algorithm is kind of manipulating the data in a way to look to sort of accentuate patterns that may be present. And so the black box part of any machine learning algorithm, so the blue circles represent your input parameters, those are your X's, the green circle represents your output or your response. That's your Y. And then in the middle is usually just the black box that connects the two. And this is why, so like when a human lost to a computer in Go, there was a black box that had learned strategies to play Go, the game. And all those strategies were captured in the hidden layer. In the end, what you're doing is you're generating a response surface. And so your various input, the variables that parameterize your output are on the x-axis, and then your response is on the y. The reason that you need so much data in machine learning is because if I only did experiments in the corners of my box, and then I asked the algorithm, we'll make a prediction for what's going on in the middle, it's probably going to say, well, you measured basically the same for values in the corners, so in the middle has got to be the same. So the only way the algorithm knows that there are all these hills and valleys in the response surface is if you go in and measure it. And if you're working in a 5 or 10 dimensional space, the number of points that you need is a lot. So that's called the crisis, in machine learning, that's called the crisis of dimensionality, and it's basically like we will always underestimate the amount of data that it needs to really map out a high dimensional space. So the question is, well, so how do we normally do machine learning? So this is a paper that showed up a couple of years ago, and it's really kind of a benchmark study and one of the first real kind of benchmark studies of applying machine learning to kind of the kind of workhorse problem in cement and concrete, which is predicting the compressive strength. And so Sant and then Boshi and Sant at UCLA, basically there's a very famous data set, the Yay data sets, where they had of order 1,000 different concrete samples, and they were parameterized by eight different variables. And so these were things like, the water to cementitious ratio, how much fly ash was in there, how much water reducing agent was in there, how much air was in there. And so for these 1,000 samples, what you see are basically all these different, the correlations between the compressive strength and, say, in the top left, that's the water to cementitious ratio. And so obviously, we know that as we increase the amount of water, the compressive strength goes down. That makes sense. But we see basically less clear relationships with these other variables. So when the authors when they went through and built this machine learning, they built basically a bunch of machine learning models, and they did some manipulations. It wasn't, you have to actually look to a different paper to see the kind of true output of, or to get a more accurate view of what they actually did. So the real test the first real test of most machine learning models is something called a parity plot. In a parity plot, what you do is you actually just, your algorithm is going to make predictions. You come up with a model, and the model is going to make a quantitative prediction for the output of every possible input. So what you do is once you've got your model, you then go and you put all your data points into it, and you get a prediction for the value. So you take all your X's in the different combinations, and you put them back into the model, and then you get you get a prediction for the output. And you plot your predictions against the actual points. And so if your model is perfect, you're going to see a straight line. And usually the R squared, which is just a reflection of the percentage of the variance that the model's capturing, is sort of the first metric that people look at. And in most settings, certainly among academicians, if you've got an R squared less than 0.8, nobody's really interested. In industry settings, if your R squared is 0.7, nobody's really interested. And so the fact that they saw an R squared of about 0.6 was not amazing. And so there was nothing wrong. This was a really good study. There was nothing wrong with the study. The real problem with this, though, is that the algorithm didn't really know what any of these variables were. All it knew was that if air was closer to 7%, the compressive strength was weaker. If it was at 5%, if there's less water, et cetera. But it's like, you've basically got these 8 variables, and it's like, there's this Dr. Seuss book that's like thing 1 and thing 2. We've got thing 1 through thing 8, and all the algorithm is doing is looking for patterns in this. It doesn't really know. It's working in this 8-dimensional space. It doesn't really know anything about what it's looking at. And so the fact that you're seeing an R squared that's not great is in many ways, it's in some ways a reflection of the high level of variability in terms of like which water reducing agent did you use. And then the other piece of it is just for an 8-dimensional space, 1,000 data points is not that much, or is not that many, okay? So getting back to our basic question, can we do machine learning on 50 samples? That seems bonkers. You try weird things after you get tenure. So the type of model that we really have gotten focused on, or what we've yet to come up with settle on a reasonable name. My name this week is an explicit hidden variable model. So going back to the structure, so input here in blue, output in green, the hidden layer is normally just all the math that the algorithm does to manipulate the data. Another name for hidden variables, though, are latent variables. And scientists and engineers are kind of familiar with latent variables. These are basically, you think you're changing one. You go into the lab and you physically change one variable and you see a difference in response. The latent variable is a more mechanistic variable that says, okay, you swapped in a different monomer, so one thing for another, but that other monomer had sulfonate groups, not carboxylate groups, and that led to all sorts of different changes. And so the hidden variables are the ones that have a more mechanistic impact on the response. And what we realize, and I'll kind of elaborate as we go along, is that we can actually estimate hidden variables or latent variables, and we can actually build models based on these, and it turns out the models are much, much more accurate. There's no such thing as a free lunch, and there's a lot of extra work that has to go into these, and so, but you're not locked out of machine learning if you only have 20 samples or 50 samples or 12 samples even. Okay, so I'll speak to some of these advantages to hidden variable models, but I'll note that you need additional data, you need empirical models, you actually have to know something about the system. You could be stuck if it turns out you have an incomplete understanding of it. And then finally, there's a lurking issue of bias, which I'll sort of return to. So getting back to LC3, this was the composition space that we explored. We did this work. We wanted a first kind of benchmark study to really understand forces without the influence of chemical admixtures. And so what that meant was that we're operating at much higher levels of water than you would normally operate. But we needed this range in order to get workability out of as many of the samples as possible. But we looked at these three different ratios of the metakaolin and the limestone, different ratios of water to cementitious or solids, 3 different limestone particle sizes, and then 4 different levels of added gypsum. And then we did both mini slump measurements, and then as well as steady shear rheology measurements, where we could separately measure the slope is the viscosity, and the intercept is the yield stress of the paste. Okay. And so I'm just going to focus on where the blue curve meets the y-axis, the yield stress, and that's the thing that we're going to focus on modeling here. Okay. So if we read through the literature and look on the right-hand side, if we read through the literature, these are all, in terms of things where, again, we're holding the type of clay constant. So we're taking, so the zeta potential for the clays is all the same because it's only one clay. And so some of those variables that I talked about at the beginning are not going to enter into the model at this point. But the things that are going to be relevant are, certainly the water to solids ratio is a big factor. And so rather than calling it that thing that's winds up being water to solid, there are different ways that you can look at the impact of increasing the amount of water. You can look at something called a packing index, which has a more complicated form, or particle density, which has a simpler form, and then a solid volume concentration is a third kind of metric for that. And then we can look at the proportion, the volume proportions of metakaolin to limestone, and then also the alumina to sulfate ratio. So these are all variables that we claim are really hidden or latent variables that we can actually get insight into. We can actually directly calculate all of these based on the composition. But that when we're making changes to the formulation here, what we're saying is that there's some combination of these latent variables that are actually governing it. The different performance metrics that we're going to calculate are going to be things like the fit and the parity, the R squared in the parity matrix, or the root mean squared error, which is just the difference in the model versus the actual square divided by the number of samples, square root. Okay. And then most machine learning algorithms, there are two steps to train the algorithm. The first, so if I have 100 data points, usually what you'll do is you'll randomly pick 75 of those data points and you do what's called training. And that's basically where I've got a model and then I start showing it 75 data points and it's optimizing different parameters to fit those data points as well as possible. And then I reserve the other 25 samples to do testing, so I'll take that model and then I'll just see how accurate my predictions are for the other 25. And so you can do this hundreds of times for a given data set by just taking different, random selections of those. But there's a training part and a testing part. If anyone just is reporting a training error, they're probably hiding something. And then really then in order to build these latent variable models, what you need to do is in this case, you do a lot of different yield stress models, or measurements rather, and then in this case, we're just calculating the solid volume concentration, and we're looking to see are there correlations between the yield stress and the solid volume concentration. We note here that these points here are all going up. So at a constant solid volume concentration, they're all going up because they all have increasing amounts of gypsum in them. The other way. The increasing gypsum is taking it down this way, and so So this is already not a good sign for this variable. If it's missing a trend like that, we're looking for slightly cleaner separation, slightly cleaner trend lines. So this is just a reformulation of plotting of some of these variables, and we see a fair bit of scatter. You've seen this plot before, but this is the yield stress as a function of both the relative amounts of limestone and calcine and metakaolin in this case as a function of the water-to-solid ratio. And again, we're seeing a nice strong correlation here, both in terms of the mineral composition and then also in terms of the amount of water. We do note that so you see a larger, so if I go, let's see, if I'm at a higher water to solid ratio, I see a different relationship between the blue one and the green one, which have flipped amounts of metakaolin than I do over here at the low. And so we think and we interpreted that as meaning that that as we are forcing the particles to be closer together, this potential electrostatic interactions again, coming from the zeta potential of the clay particles, is coming through and sort of tuning some of these. So it's not like we're immune to sort of zeta potential effects, but the basic trends are still dominated by water and how much of which one. And then we also see that as we go from the very finest limestone to the coarsest, we see decreases in the yield stress. And then finally, the gypsum content. So the sulfate balance in this case is a strong determinant of the yield stress, and we kind of plateau at about 5% gypsum, which is what most other people have measured. So the way that these models work is, if I start with, so if you're going to do a traditional model, any model to predict, in this case, the yield stress as a function of compositional variables, sample 1 had a certain combination of Portland cement, metakaolin, this much 25 micron limestone, blah, blah, blah. And I would write the yield stress value here. So what I'm looking for is a function, yield stress as a function of these. And I'm going to do a regression, and it's really going to be parameterized by what is it. When we do like these kinds of measurements here, what we're doing is essentially we're relabeling this by stuff we can calculate. So a packing index, this aluminum to sulfate ratio, the number density, the particle density, the ratio of metakaolin to limestone, et cetera. So these are all latent variables, and if I were to explain to you, well, how does LC3 rheology work? I wouldn't necessarily use this language. I would use this language, and so this is a model that's really parameterized by trying to answer the question, how does it work? Okay. And so we're still going to do a regression, but here in this case, sample 1 is not labeled by how much cement is there, but what was its packing index? What is the value of that? And then we'll do the regression. Okay. And then there was the machine learning step, and I'm basically skipping that. We're using in this case, so like. At the LC3 conference, I went to a very interesting poster on using machine learning to predict compressive strength of LC3, and the folks there had about 100 data points, and they augmented it through some numerical sleight of hand. That's fine. And then they basically took this augmented data set and they threw it against 120 different machine learning algorithms, because that's what you can get in Python at this point. And then they picked the one that had the highest R squared, and that was their result. And so I would kind of call that what I would call that is basically R squared engineering. Is I have no idea how these algorithms work. I mean, they probably did, but that wasn't conveyed on the poster. And I'm just really fishing for the most accurate model I can get. I don't know if I learned anything. Maybe I did, maybe I didn't. But we generally don't spend a lot of time picking, one model versus another. We like support vector regression there are a couple reasons why it's a good tool for these types of data sets. But there are things that you can do. There are things that you can do on this side that you can't do on this side. So one of the really critical steps in machine learning is what's called feature selection. In feature selection, what you're trying to do, and this is something people in statistics who've done statistical modeling forever have always done, you're basically trying to ask the question, well, which of my variables really matter and which ones don't I need to build an accurate model? The problem with compositional models is I can't take air out of my model for concrete strength, right? I can't take I can't take gypsum out of this model. I need gypsum. I need all of these components in there. Every component matters. But when I have it in terms of force, latent variables, hidden variables, forces, et cetera, really every one of these is a hypothesis, and I could be wrong. And so there are statistical ways that these algorithms will go through and say, well, I know you said that you thought you needed you know, this volume fraction, but you don't. And if you take that out, you can actually build a better model than leaving it in. And so it turned out that the solid volume concentration of particles was not necessary. We thought it would be, and we included that in the model. The model then kicked it out. And so the nice thing, and so we did a fairly simple model where we just said, using support vector regression, it found that these other four mattered. The most important factor was this packing index. The second most was the aluminum to sulfate ratio. The third most was the total particle density, and then the last was the metakaolin to limestone ratio. So if you want to know what factors for these compositions of LC3, what factors matter, packing is first, sulfate balance is second, et cetera. When we do the parity plot on the training, so the part that we held out, so this is, again, the more meaningful test of how these algorithms work. And this is, again, this is just an average representative one. The plot here, the R squared, is actually taken over the average of all of the test train splits that we did. The R squared is 0.97. So at least in terms of that metric, even with just 50 samples, we are way higher than these kind of these compositional models that are that have 10 or 100 times as much data. And so we claim that the reason is because of the parameterization by these latent variables is much more powerful than by compositional variables.
Can I ask you a question?
Please.
The packing index here have a maximum packing, which is then the same regardless of the size distribution?
It's here. So this beta I we assumed was, I think, 0.74 for all of the samples. So it's like a maximum packing fraction. This, yeah.
And then you're looking for linear functions of these parameters in all cases, or do you have
well, it's the support vector. So support vector regression is not actually a linear regression. There's something called a kernel in it, which is basically how we're picking, how we're setting the similarity of two different data points, and that winds up being an additional parameter. So I didn't go into an explanation of how SVR works, but it's actually not. There are simpler models that we actually start with that are based on linear regression, and that would actually literally just be yield stress equals a linear function of a coefficient times k. A coefficient times that ratio, plus a coefficient times that ratio, plus a coefficient times the solid volume concentration, et cetera. So this winds up not being just a linear function. There's an additional transformation that the algorithm is doing, but it's a sort of kind of a once all the parameters and hyperparameters have been set, then the model is static. It basically then in theory, you could make predictions on any new mix. It should be able to accurately predict what that mix value is. And then in theory, you can actually invert it such that if you wanted a certain yield stress, you could ask the algorithm, hey, give me 10 or 100 different mixes that, I can constrain all the different compositions and still give you 10 or 100 different compositions that'll have that yield stress. So it still acts like a function, but it's just more complicated than just than linear regression. Okay. So basically, the conclusions of this part are that when we see this design space, we think in terms of those variables, that these are the variables that really govern this, and then this particular way of developing a functional relationship using support vector regression resulted in a very accurate model. The next steps are, actually, I met, I think you're a former student here, Anna Szabo, who's, a very impressive rheologist, and I explained some of what we were doing, and she's like, that's it? that's the only thing you've done? So what she's recognizing was that there's a huge, LC3 has got this huge space because the clay, German clay is different than Swedish, as we heard at the conference, German clay is different than Swedish clay, is different than Syrian clay, is different than Indian clay, et cetera. So there are all these additional variables that really go into predicting quite generally what the properties of LC3. And so we are looking to extend this to different Portland cements and different clays in particular. So illites and muscovites and things like that. We can, and we could already invert this particular model, but we'd like to be inverting that model. And then in some ways, almost larger challenge is then figuring out the interactions with chemical admixtures like superplasticizers and things like that. And so this is just this is the type of data that we would like to get our hands on. This is from a group in Munich that did a very nice study on looking at some different LC3 type formulations and starting to think, talk in terms of what we would actually refer to as latent variables. So I'm going to quickly shift gears and so really in the first part I just talked about let's just build an accurate model in terms of latent variables and then see if we can we can really use that model to really understand the forces that govern the properties of a complex material like LC3 paste. Ultimately, we actually do want the model to be parameterized by experimental variables. Understanding is nice, but I'd actually like to have a design tool. And so the goals are really, we'd like to be able to parameterize by composition, by chemistry. So, which molecules that I take, formulation, how much are mixed in, and then even how they're processed. And then we have these kind of larger goals as far as making some accurate predictions from small data sets. And so this was the first paper that we did where we elaborated this algorithm. We call it an algorithm called hierarchical machine learning. So we're interested in using this in I'm interested in using this in admixture design. That was kind of where we got our start in all of this. And so there are two ways that you can think about doing kind of admixture design. One way is doing molecular design, which is done very well here in your labs. And then really what you're doing in the case of polymer chemistry is you're trying to take certain monomers and organize them certain ways, either on average or very specifically using controlled radical polymerization or something else. And so this would be something called a discrete combinatorial system. And so language works like this. So if you want to read a few hundred pages about mostly how the English language works, this is a really good book. But sentences, it turns out, are built from combinations of noun and verb phrases. So the sentence would be like in this metaphor, the sentence is like a polymer. The noun phrase and the verb phrases that we're hooking together are the monomers, and then these phrases are actually composed of words. So John hit the ball. So John is a standalone noun phrase. In the verb phrase, hit is the verb, and then this acts on another noun phrase, which is the ball. And so taking this metaphor one step further, the functional groups are what we actually need, what we're going to try and identify as being useful. Then what we're going to need to do, as I'll show you in the approach that we took, is we have to organize them sensibly into monomers and then figure out how to build these into polymers. So this is molecular design. On the other side would be formulation design. And there the goal is, hey, this polymer does these things well. This polymer does other things well. If I want the best of both worlds, I'll mix them. And that's really how formulation design, and ultimately, that's like a blending system. And so here what we have, so you have countably infinite number of, technically you can only have maybe 10 to the 60 different molecules, depending on how you limit molecular weight, but it's close enough to infinity. You also have an infinite number of outputs, but they're continuous. They're basically uncountable, and so color works like this. And so, if I wanted to have, an output that was some flavor of orange, I'd be looking at combinations of yellow and red. And so that would be like, taking polymer 1 and polymer 2 and figuring out the right way to blend them. And so I'll tell you about some early work that we did here, and then the very painful early steps in how we're implementing it over here. So a very simplified view of how we think superplasticizers work is like a polycarboxylate ether. It's got its anchor groups, these carboxylate groups. They will stick to the surface of a hydrating cement particle. And then you've got these pendant peg chains, and they stick out. And then this increases the electrosteric interactions between particles. And so the adsorption of these changes the interparticle potential. And so we see different flavors there are different types of superplasticizers or plasticizers or water-reducing agents, and they all have kind of different combinations of different ways that they will balance sort of, sticking to the surface and then changing the interactions between the particles. In the first work that we did, we got interested in this basic question of, can we do molecular design with a broader range of colloidal forces? So rather than just electrostatic, so charged carboxylate versus sulfonate, and electrosteric, which is PEG, we were also interested in the kind of basic question of what do the non-adsorbed chains do? There's been some study of that. So the Planck group has done a lot of nice work looking at, sort of inferring the importance of depletion forces, but then there are also viscous forces. And we were wondering if those would be important. And so really, rather than, a sort of particle-only view of the function, we're interested in changing particle forces, solution-mediated forces, and then even forces that bridge particles and solutions. So on the right here is sort of how and hopefully you're starting to get the hang of how these diagrams work. So the output I'm trying to measure is SLUMP. In the studies that we started here, this was sort of it was just a blend of a type 1 cement and with 15% metakaolin, constant amount of water, and constant loading of superplasticizer, so that every sample had these constant. And so even though the experimental variables included cement never changed, and so I can just keep it out of the model. The only thing that's changing we had a series of superplasticizers, which I'll show you on the next slide. And what we did was, because we had some that were based on lignin, which is hard to characterize, we parameterized it just in terms of the functional groups. And so these would be like the words that we're going to try and build phrases out of. So we had for every mix had a different superplasticizer in it at a constant amount. And so the only thing that was changing was the relative amounts of these different functional groups. And then we were trying to predict the slump, the mini slump of these. And then we were looking at these 4 colloidal forces, viscosity, the osmotic pressure, which is we took as the second virial coefficient, the zeta potential, and then sedimentation was sort of a poor man's approximation to a way of estimating an electrosteric effect. So what we did here was we did mostly measurements. So the first 3 measurements were actually only polymers done in solution. So there was no cement around. And so ultimately, and then the last one had a very low concentration of ceramic particles in it to do these sedimentation experiments. And so ultimately what we're trying to do is, so in the last talk, or in the last part, I said, rather than identifying every sample by the compositional variables in this case, what we're going to do is we're going to label it by estimates for the physicochemical force, these 4 physicochemical forces, and then there was an additional one, which is the amount of adsorption, which is kind of a hidden variable. And what that does, a hidden variable, and what that does is the more that is more polymer that's adsorbed, the less that these solution forces will take into effect, and vice versa. Okay. But again, what we want to do is we actually want to come up with essentially a digital model of the colloidal forces that are acting in each of these pastes and use that to build our model. Sorry. In the last part of the talk, I showed that we could actually do a surprisingly good job of predicting something complicated like slump or yield stress based on these latent variables. The thing that was missing from that, though, that Anna actually figured out, was that I didn't actually tie it back into composition. And so my response surface was ultimately still just parameterized by latent variables. And so if I want to tie this back into composition, I need a map. And so we generated the simplest possible map, which was, we had in our training set, we had more than 7, but here I've got listed 7 of the polymers that we used. And then we decomposed them into estimates of the fraction of each of these functional groups, and then a flag for was it cross-linked or linear. And then we essentially did a regression, basically a least squares relationship to attempted across all the polymers in this training set to say what was the contribution of a sulfonate group to the intrinsic viscosity. So sulfonate groups are strongly solubilizing. They tend to reduce aggregation. It kind of sort of makes sense that the more sulfonate you've got for constant molecular weight, the lower the lower the intrinsic viscosity. Some of these make more sense than others, but essentially what we're trying to do, this is essentially our map of going from, we're going to connect each of those forces to composition through a really super simple least squares regression. And so my students get nervous when I say this, but in some ways, hierarchical machine learning is just a series of terrible approximations, and you sort of keep your fingers crossed that you'll get to an interesting place at the end. But you're really trying to, essentially what we're going to do is we're going to figure out slump as a function of these forces. We'll get a function for that. Then we'll figure out the forces as a function of composition. Then I can reparameterize the slump in terms of the forces in terms of composition, and I can get rid of the forces entirely. So we can do a simpler form of regression of feature selection and regression called lasso, which stands for least absolute shrinkage and selection operator. But it's basically a way of coming up with, if I ignore this term here, finding the coefficients beta that minimize the difference of the square of this difference is linear regression. In lasso, what you do is you add an additional term, which is essentially just the sum of the magnitude of the coefficients times lambda, which is called a hyperparameter. So the bigger lambda is, the more that it will penalize a complex model that's got a bunch of different coefficients in it, a bunch of different terms, and that will make it simpler. And so what you're looking to do is, if my model is way too simple, like I've only got one variable, it's not going to be especially accurate. In my training, as I start to add more and more terms, I get more accurate, but what I've done is the models wind up being completely specific for exactly those data. So when I go from training to testing, I get, and I look at the test score has started to shoot up. And so all this is doing is basically right-sizing your model in terms of its complexity. When we do this, the colloidal forces that seem to govern the slump of this blend of metakaolin and Portland cement, the way to read this is it's just a function of the viscosity, the zeta potential, the product of the zeta potential and this sort of electrosteric coefficient, and then the product of the viscosity and this electrosteric coefficient. One acting on metakaolin and the other appearing to focus more on the Portland cement side. That we'd be less confident on. If we just look at the first two terms, though, what this is saying is that, this term in particular right here is saying that it's predicting that as I increase the viscosity of the pore solution, I will actually increase the slump. The consequences of this term are a little bit murky. We had some thoughts on that, but I will defer that to later. But if we then take this formula here and reparameterize, so we have, from the previous slide, we have a model for how the viscosity depends on composition. If I reparameterize every one of these terms by its compositional terms, I can come up with Yeah, please.
Viscosity goes up, that means the polymer is not absorbing. So are you basically saying it's a problem with absorption there?
What it's saying here is that for combinations of metakaolin and Portland cement, and also the fact that this has the largest coefficient means that this is the dominant force for this blend. And so what it's saying is it's very specific to this blend, and as we increase the viscosity, we will increase the slump.
This is the viscosity of the paste or the continuous phase?
So it would be the viscosity of the pore solution.
Right. So that will go up if the polymer is not absorbing.
Right.
So
or if you pick a different polymer.
right.
So what the algorithm actually output was just a combination of, sulfonate groups, aromatic groups, carboxylate groups, alkane groups, PEG groups, et cetera. So those were like a jumble of words that we basically had to turn into phrases. For example, like the sulfonates and these phenyl groups showed up at about the same levels. And so we looked at that and said, well, let's try a styrene sulfonate because that would match those together, and that's a sensible thing. So we didn't try to pair the sulfonate and the PEG, for example. And so there was a lot of, it wasn't strictly just us doing exactly what the algorithm said. It just sort of gave us guidance on the composition that would be useful. So when we made this polymer, we translated the functional groups that it wanted into monomers, made a polymer. One interesting thing was it was very rich in styrene sulfonate. So over half the monomers were styrene sulfonate. The interesting thing about styrene sulfonate is that it has a very high intrinsic viscosity. The viscosity of this polymer was, the intrinsic viscosity, so like viscosity per chain, is at least 10 times greater than that of PCEs, for example. And that has a lot to do with sort of the stiffening effects of this monomer and chain interactions and things like that. And so it still had some of these kind of anchoring and PEG groups, but it was sort of balancing a very high, this monomer gave us this very high intrinsic viscosity and a reasonably positive A2, and kind of matched some of these other requirements, but it was sort of the closest that can't be followed this mapping. The interesting thing that we saw here that was, well, basically what we observed was that if you took the same polymer and you put it into just pure Portland cement, it didn't seem to do much plasticizing. There was something about the way that this polymer was just particularly interacting with the Portland cement, the metakaolin parts that were sort of most efficacious. That there was obviously some plasticization. You still had 85% Portland cement, but the big, the bump seemed to be very specific for metakaolin. So there were some issues with shall we say, the cement itself that we were using, but that we were reproducibly seeing this. And so what this result is just highlighting is sort of the methodology for doing molecular design here based on the data that you have at hand. Okay. And so I'm just going to show very briefly how we're starting to do formulation design. And so again, we've got a training set, and these are some of the elements of it. These are different polymers here. So we've got, in this case, so these are established plasticizers. Polystyrene sulfonate we're using in its pure form. It's actually used as a dispersant for clay slurries. And then hydroxypropylmethylcellulose is a viscosity modifier. And so I've kind of color-coded as a heat map, sort of like PCEs obviously have a strong electrosteric effect. The hydroxypropylmethylcellulose has a solution viscosity that's incredibly high. It turns out the polystyrene sulfonate has a reasonably high solution viscosity as well, et cetera. And so what we're doing in terms of forces is we're starting to fill out a matrix of different combinations of these solution forces to see how well we can actually start to, instead of, again, doing polymer synthesis, what we actually want to do is we want to start looking at formulation design, but guided by rather these forces here. And so these experiments are ongoing. But again, so now what we're doing is we're actually getting back to that rheology curve. We're actually looking at at the bottom curve and the effects of the superplasticizers on both the slope, which is the viscosity, and the intercept, which is the yield stress of the as well as the mini paste. And so we're holding, now we're going back to holding most of the cement composition part constant and looking at different doses of these different polymers, and then also looking at blends to see how well the model actually starts to predict looking for basically some synergies here. And so, again, we're seeing sort of lots of patterns of these. In the ones that I'm showing here, MG3030 is just sort of a garden variety PCE that we got from Master Builder. It's not specific for LC3s. It works reasonably well at these doses, though. And so for most of these samples here that we have plotted up, what we're seeing is that on its own it works fine, and if you add anything else, it works worse. That's not, in this case, always true. That hiding in the data that I haven't shown here, there are actually examples where if I add, for example, the viscosity modifier, the hydroxypropylmethylcellulose, we actually start to see some synergies with some of these other components. Interestingly, whether you use the time-dependent release version or not matters. But again, we're starting to accumulate data. And then just doing these sort of first bit of modeling, again, we're looking at models where it's just parameterized by these forces. We haven't gone back, we're not going back to composition. Essentially what we're seeing is that with a relatively small training set, about 15 samples, we actually do a reasonably good job of predicting the post-yield viscosity. But the yield stress model is actually relatively weak. And to the extent that mini slump, is first determined by yield stress, but I guess we had a discussion about this at lunch. Our sense is that the plastic viscosity still matters as a component to that. We do okay with the mini slump. So right now, what we're seeing is more accurate. We're more accurately capturing the responses of the viscosity, and so. This kind of gets back to what I originally was talking about in terms of model. The problem with these is the model bias, in that if there are other forces that work here, we don't know about them yet, and so we're still looking at how we will. Basically, the underlying forces, the latent variables that govern this response. Okay, so this is the end of the cement part of the talk. I just want to thank RPE for funding, these folks for materials. Kim's in the middle there. Oljan is the student that led a lot of this work. He's going to be starting work at GCP Saint-Gobain next month, so we're excited for him. But they've been great collaborators in these studies. I'm just going to pivot a couple things, highlight a couple things real quick, and then I'll wrap up. I know I'm running over. The first is that we can use this algorithm in additive manufacturing, and in particular, so this was work done in 3D bioprinting, but it is not. It has some similarities and some significant differences with how you guys are doing additive manufacturing of cement and concrete. If you want to print a viscoelastic fluid, the main way that this is, so like a biopolymer, for example, like if I wanted to print an artificial organ or something like that, because it has this, it tends to be more viscous, I can't just print it as you are. There aren't tricks necessarily for printing it as you're doing cement and concrete. And so one way of doing it is actually printing it into an aqueous bath that has a yield stress due to suspended collagen or or other charged polymers. And so essentially here what we've got is we have material variables, so like what's the material, what's the ink, what's the material in the bath. We've got formulation variables, which are like what's the concentration of the ink, what's the concentration of the bath, and then process variables, which are things like, how fast is, what's the extrusion rate and how fast is the needle rastering as it makes this form. And so what we showed a couple of years ago now was that we can actually start to combine these different types of variables, so concentration of ink, the velocity of the needle, the extrusion rate of the ink, and the diameter of the nozzle. These are all different flavors of variables, but the algorithm is still able to manage these, and we can actually do some optimization shown here and identify conditions where we actually will, for example, we can optimize the printing of corners versus lines. And all this is guided by, an underlying knowledge of the dependence of the viscosity on the shear rate and the concentration, for example. Okay. The other piece I wanted to just spend like 3 slides on is just the company. So Barnabas is my machine learning guru, and I ultimately wound up, we were trying to do sponsored research with the company, and then when the university and the company couldn't reach terms, we just started a separate company called ANSATZ. And so we've mostly operated as a consulting service. We're starting to do some training, and then we're working on developing software. In the chemical and materials industries, there are 2 kinds of tasks that you generally you have to do in research and or development. The first is continuously tailoring some solution or meeting a new product requirement. And then the second is just optimizing something that's super complicated. In the first case we'd like to reduce the cycle times from weeks to days, or in other cases, hours to seconds. And then in the second case, it's really a question of we want to do it with as few samples as possible. But the idea is that we want an algorithm to be managing all the different aspects of these processes. And so just some of the work that we've done through the company. So we're working, so the companies that we work with generally remain, don't want to show up on our website. The first company is Procter & Gamble. They make kind of, at least in the United States, they basically make everything in your house. So like shampoos and detergents and, some foods and things like that. And so they're interested, the problem that they asked us to work on is they are trying to make their shampoos all bio-based, or as much bio-based as possible. And so they're taking out all the petroleum-derived thickeners and things like that and replacing them with cellulose and different combinations of surfactants. And so the question there was, well, how can I reformulate the shampoos such that I get, such that I have the same rheological characteristics, but most of the components came from plants. The second is with a Japanese company called Taiyo. So you know how circuit boards are green. Taiyo makes 80% of the green in the world. And their customers are starting. So what the green does is it prevents the solder that you're using to make connections on your circuit board from running around and short-circuiting your circuit. Taiyo's clients are starting to do inkjet printing to just deposit the green exactly where they want it. And so they asked us to basically make a version of their ink, or formulate a version of their ink that would have 0 defects. And so we've done that with them. And then the third is color matching, which is important for paint companies. And so the question is, if I want to match, the blood orange of that Porsche, but I've only got, the Porsche from the 60s, I've only got current pigments. What combination of those pigments could I use to exactly match that? And so what the algorithm needs to do is given the reflectance spectrum on the car, what do I, pick 5 to 10 pigments and tell me how much of each one to use, such that we get a perfect match. And so the algorithm is actually done quite well. Okay. So I will just close thanking a few folks from CMU, from Georgia Tech. Covestro has been a good partner for us. It's been certainly an interesting journey. I'd like to thank these folks for their support. And then these are different stages of the group. And we have we have Halloween where we have every year a semi-competitive pumpkin carving party. And so that's a picture from one year. I've worked with some great students. It's been a pleasure to be there at the university. And I'm sorry for all the technical difficulties. I probably ran late, but I really appreciate the invitation, and I'm happy to answer any questions.
Well, thank you very much. There's a whole bunch of things to discuss. I think most of your results there with pastes with metakaolin in addition to the cement, right?
Right.
That introduces all kinds of questions of what might be going on there.
Yes.
I think it's, questions for Newell? Yeah. Wait.
Good catch.
Hi. It works.
Yeah, the top.
How, from a computation point of view, how expensive is it to run the model, like the machine learning model?
Oh.
Can I run it on a normal laptop, or do
Yeah.
I need a
No,
like
I mean,
cluster?
Python outputs how long it took to run something, and most things are seconds. There's some that are involve a little more matrix algebra, and those will be like a minute. You know, if it's 50 samples, your laptop will be fine. We have a server at the in our lab for kind of some other problems that are bigger data sets, but everything here, your laptop is fine.
Okay. And the latent variables, like you can either give us inputs, so powder, air, and water, or packing density, packing index, and these kinds of things. But it's still like the human who does the translation between like amount of powder and packing index.
Yeah.
So it's basically a different type of variable. Like, but the algorithm is the same, like from a math point of view.
Yep.
Okay.
Yeah. So and really, I mean, certainly with something like the first project, I mean, people have thought very deeply about the factors that govern, say, LC3, the rheology of LC3 or Portland cement in general, and really we were just taking what we had found in the literature and using those as the variables in our models. So that part, we can't sort of claim a big contribution. It's just, but essentially what these folks were observing, there would be a separate paper on, oh, look, packing index, the yield stress or the mini slump is very strongly correlated with the packing index. And so it's those types of established correlations that we then lift and use for our own purposes.
Yeah. Okay. Thanks.
Other questions?
Could you go to the slides of 23? Thank you.
No, sorry. Yeah.
Maybe 22 about the experiment. Sedimentation to obtain the interparticle force, I think. How could you link the sedimentation experiment to obtain the force?
So that's a good question. So you would definitely know better than I, but I don't know any way that, the belief is that an adsorbed PCE is changing the interparticle potential between two hydrating particles. And I know you've done some direct measurements of that, but I don't know if we didn't see any way to extend those theories to this. There was no sort of parameter that we felt like we could lift as far as making a generalized predict, because we wanted to do the same type of prediction for, things that weren't PCE. And so what we did with sedimentation, this is like the worst part of our experimental, but we just haven't figured out better ways of doing it. Basically what you do is you take a dilute solution of a ceramic powder, you add the polymer dispersant to it. And then what you'll see is if you adjust the concentrations of everything just right, and you let it sediment, that you'll see different sort of equilibrium sediment heights. And that will correlate with things like the extent of aggregation, which will correlate with changes in interparticle potential. Really, all we were looking for was something that was kind of pointing us in. We could do a rank ordering of like a dispersing effect, but it wasn't. This was definitely not brilliant.
So did you measure the volume fraction at different heights in your sediment or not? The volume fraction of solids in the.
Oh yeah. Mm-hmm. At different heights. No.
Yeah. Okay.
Okay. Is that?
Yeah.
That would be advised.
Yeah. Well, if you have time, maybe. I don't have afterwards, but we can chat also later. But Shengnan's got some quite cool results on the yield stress modeling and the role of percolation threshold, which doesn't appear in your models, I think. Right?
No.
So
no.
maybe we can discuss. There's quite a lot of data.
Okay. No, I'd love to see, because it's really like every time we come back to this. I mean, the one reason we got away from admixtures is like it gets messy in the middle,
right?
And we just need better methods. And
right. So we have a kind of a cool approach to start looking then at from limestone, cement, and then the combination. But as soon as you go to the combination, it becomes messy again. But we have a couple interesting results which kind of point to how the polymer is changing the percolation threshold, but not the maximum packing. And that, I think, would potentially be like hidden factors which are not there, which might relate to one of the things you've been measuring, but it would.
Right.
So
right.
If you have a bit of time, you can.
No, I'd love to learn more about that.
Thank you.
Or later,
yeah.
or
right.
email. I should say.
Time, yeah. Other questions? Who wants to receive the cube? Yes. Throw it. No, you have to throw it. You have to throw it. Yeah.
Good catch.
Great. Thank you for your talk. And so I have a question for you around the topic of scientific machine learning, because I think that this is it goes in this very much in this direction with physics-informed models. And so a colleague of ours, Michael Kraus, works very much in this direction.
The bridge guy?
Yes, exactly. And so I was just curious if you have, so they recently published a paper on physics-informed neural networks. Have you explored that? Because it seems it could be very readily applied, because you're already looking at these physics-informed models. And dimensionality, or I guess data reduction, essentially.
Yeah. So there's been a lot of work in that area, and there are a lot of very both clever and smart ways of embedding kind of different forms of domain knowledge. I mean, physics, because it's all mathematically based, works very well for this. But the reality is that even when there are other ways that you can embed even sort of like, empirical knowledge of how stuff works into these algorithms. And so I think I've seen the paper that you're talking about, and really it's just at the end, when you really look at how the physics is being embedded or the chemistry is being embedded, they wind up not being that different. I mean, there's some ways that are very different in terms of like different similarity metrics in terms of, again, I was mentioning one thing that this algorithm was good at, that one reason we like support vector regression is because there was a way of tuning the relative similarity between points. There are more physics-based ways of doing that are probably a little bit more rigorous, but you have to know a lot about, very exactly about how the system works. And so, in general, we're fans of that stuff, and certainly we wouldn't point to this as being necessarily better than anything else. It's just, partially given the kind of underlying messiness of kind of systems that scale, go from molecular scales to sort of macroscopic scales. You need something that can kind of span those.